So we're going to talk again about Gibbs free energy. Fourth time's a charm, right? Okay. So again, we want to be able to determine ultimately whether a reaction is spontaneous or not, whether it will happen spontaneously or whether we have to, do something to it to get it to happen. So Gibbs free energy is a really useful tool to help us figure that out, because what it does is it combines the ideas of enthalpy and entropy into one equation. Okay, and so the way that this kind of works, you may have noticed this when we talked about it the other day. Do you guys remember in the video when we talked about a solution that dissolves? Now, even though sometimes it has to, even though that's an endothermic reaction sometimes, and that it absorbs energy, because there's an increase in disorder, it will still happen spontaneously. There's certain things. So actually, this is a lot of solids. Will actually, their dissolving will be an endothermic process. And that's okay, because the disorder is increasing, okay? So it kind of offsets that, having to absorb energy from the surroundings thing. By the same token, there are certain reactions that can happen that would actually decrease the entropy. In other words, they would make a system more ordered. But in order to do that, they're going to give off heat. They have to, okay? In order for that to happen spontaneously. So any spontaneous reaction where there's more order in the system at the end, it's going to be highly exothermic. Okay, it's going to give off heat. And an example of that is sodium chloride forming. So sodium chloride forms from solid sodium and chlorine gas, right? So you have a solid, you have a gas, and when you end up making that reaction, you end up with sodium chloride, which is a solid, right? So that's a decrease in entropy. But when those two things come together, that's a highly exothermic reaction, so it still happens. The fact that it's exothermic, the enthalpy there kind of offsets the decrease in entropy, okay? So these two things are kind of, sometimes they work together, sometimes they work against one another, but you can use this equation right here, the delta G equals delta H minus T delta S, to figure out whether something's going to be spontaneous or not, okay? So this is just an equation that Gibbs came up with, and he used a lot of calculus to do it. But this equation is on your equation sheet, and it's an important one, okay? This is the one that if you see a question on the AP exam about delta G, you're probably going to see at least one kind of along these lines in the course of that question, okay? So let's figure out what delta G actually tells us here. And we've got to do a little bit of playing with the variables and everything here in order to do this. You got to remember some things that we... What is going on? No. Okay, so you got to remember some things that we talked about in the last couple of days. All right, so one of the things we talked about is that the delta S of the universe, in other words, the entropy change of the universe, is equal to the delta S of the system plus the delta S of the surroundings. Okay? You guys remember talking about that? If you add those two together, now, the delta S of the universe can never, ever, ever be negative for a spontaneous process. Okay? Can never be negative for a spontaneous process. It could be 0 if it's at equilibrium, right? And it's positive for any spontaneous process, but it can't be negative. So when you add these two together for anything that's spontaneous, in order for it to occur, the delta S of the universe has to be greater than 0. Okay. Now, another way that we talked about yesterday that you could figure out the delta S of the surroundings is based on how much heat is being given off into the surroundings. Okay. So the delta S of the surroundings, you can actually calculate using this equation, okay? Negative delta H of the system divided by the temperature. Does that kind of make sense? It's the opposite of the heat change that's happening in the system. You divide that by T, because what we had, you remember when we first started talking about delta S, it's this Q reversible divided by T, right? Now way back in the 5th chapter, we talked about the fact that Q and delta H are the same thing at constant pressure. You guys remember talking about that? It's been a really long time, okay? But Q and delta H are basically the same when we're talking about a system that is at constant pressure, okay? And most of the reactions that occur are kind of out in the open, so we can assume that they're going to have a constant pressure throughout, okay? So for most of our reactions, this Q is the same thing as delta H, right? So that's where this is kind of coming from. just so that that's not coming completely out of left field here. So what you end up with here is that the delta S of the universe is equal to negative delta H of the system divided by T plus the delta S of the system. Does that make sense? And we haven't multiplied both sides by negative T yet. I'm just kind of rewriting this. Wait, I didn't have to rewrite that. It's already written. Sorry, that's this last part here. So that's this, okay? Basically, that's saying that that's equal to the delta S of the universe, okay? Maybe that's, you know, a little bit cleaner way to write it, but in order to get rid of this T down here at the bottom, if we multiply both sides by negative T, multiply this whole thing by negative T, and multiply this whole side by negative T, and you'll see why we're doing this in a second, maybe. We end up with negative T times delta S of the universe is equal to, the T is going to cancel out here along with the negative, so we just end up with delta H of the system plus, or I guess I should say minus, T times the delta S of the system. Okay? Why did I do that? What's the point of any of that? The reason I did that is because over here, delta G equals delta H minus T delta S. And this delta H is also for the system. And this delta S is for the system. If it doesn't say, then you assume it's for the system. Okay? So look, that's the same as this equation right here. So what I just said basically is that this negative T times the delta S of the universe is equal to delta G. Okay? And that's a little bit helpful because we know something about delta S of the universe, right? What did I say has to be the case for the delta S of the universe in order for a spontaneous process to occur? It has to be positive, right? So what does that mean about delta G if the delta S is positive? Look at this side of the equation, right? It's got to be negative, right? Okay? So if the delta G is negative, that means it is a spontaneous process in that direction and the reaction will occur. Okay? Now the nice thing about this is we can figure out delta H and delta S. We've been talking about how to do that, right? So if we can figure out delta H, delta S, plug it into this equation down here, if our delta G ends up being negative, that means that it is a spontaneous reaction. Okay? Now what happens if our delta G is 0? When is delta S of the universe 0? At equilibrium, right? Okay? And so that's why this is kind of useful here, because it can tell us something about delta G. So to sum that up, I think that's what we're getting at here. If the delta G is negative, then the reaction is going to be spontaneous. Okay? If the delta G is 0, then the reaction is at equilibrium. If the delta G is positive, then the reaction in the forward direction is non-spontaneous. Okay? In other words, it's not going to happen without some serious outside influence there, okay? Work has to be supplied from the surroundings to make it occur. But the reverse reaction would be spontaneous, okay? So if the forward reaction is not spontaneous, the reverse reaction is. Does that make sense? Okay. All right. For any spontaneous process at constant temperature and pressure, the free energy is always going to decrease, okay? That's where that negative comes from. So, free energy, what is it exactly? And this is the part where I'm not going to do it justice, I don't think. But the basic idea of free energy is it's the energy available to do work on the surroundings, okay? And so the more, it's sort of related to potential energy, okay? Really, the more potential energy that a particular chemical or set of chemicals has, the more free energy they have, because the more energy they have available to do work on the surroundings, okay? So when they actually react, they can do more work. So a free energy diagram over the course of a reaction, if you see something that looks like this, and again, this may not make a lot of sense, but free energy, and that's, obviously the free energy is higher at the top, lower at the bottom. And then if you just have a reaction, okay, so the reaction is progressing over time, we may start with a high degree of free energy right here, okay, so this might be the level that your reactants start at. Okay, and then what's going to happen over time as the reaction occurs, as the reaction goes from reactants to products, you're going to end up with something that kind of looks like this. Okay, and then you're going to end up with your products over here. Okay, so and this is for a spontaneous reaction. Okay, you're always going to end up with less free energy at the end than you did at the beginning for a spontaneous reaction. Okay, so this is spontaneous here. This would be the exact opposite if it was a non-spontaneous reaction. Okay, but basically what you've got here is you're going to have a decrease in your amount of free energy. Okay, in other words, as the reaction occurs, it's usually going to give off some energy into the surroundings. Okay, so the energy available to do work is decreased at that point. Okay, then as it reforms the products, now there's a little bit of free energy that gets stored back into those chemicals. Okay, so again, thinking about this kind of like potential energy, I think is useful. Okay, but notice there's this one low point down here. Okay, and this point right here, that's your equilibrium. Okay, that's the point that this reaction is going to try to get to. So you can start with an extra amount of the products here, okay? And if you start, well, you know what, we're going to look at an example of this in a second. So let me just leave this as it is, and then we'll talk about the example, and I think it'll make more sense than if I'm talking about it abstractly like this. So here's the example. N2 plus 3H2 yields 2NH3, okay? So the free energy curve for this, this is spontaneous in the direction that it's written. Okay, so it's spontaneous in this direction. And so what you're going to have here, again, I'm just going to kind of free energy. Free energy. I'm going to kind of recreate the last graph, but this time we'll be more specific instead of writing just reactants and products. This is the N2 plus the 3H2 up here, okay? And then as this reaction progresses, then you're going to end up with a certain point at which your free energy is as low as it can possibly be, okay? And then you got your 2NH3 over here. Now, you could think about this in two ways, okay? And, this is very much similar to Le Chatelier that we talked about before. If I start with all reactants here, if I just have the reactants to start out with, then which direction does this equilibrium have to go? It has to shift towards the products, right? Okay, so if I start with this, the N2 and the 3H2, okay, then it's going to react until we get to right here, okay? That's equilibrium. Okay, and at that point we will have the right concentrations of reactants and products at that temperature to be at equilibrium. Now, what if I start here instead? I start with all product. Which direction does the equilibrium have to shift? Back towards the reactants, okay? And so if I start with the NH3, then that's going to shift back until we get to equilibrium again. Okay, does that make sense? So it's kind of, there's like this low point here. It's like rolling a ball down a hill, okay? It'll stop when it gets to the bottom of the hill. That's kind of how the reaction occurs. It doesn't matter which side of the hill that you start the ball on, it's always going to roll to the low point, okay? So for an equilibrium, that's the way that it's going to work with free energy, okay? Now again, you don't necessarily have to do a whole lot with all of this. I'm just trying to give you some of the conceptual background for free energy. The calculations involved with it are not all that difficult, okay? You can figure out a standard free energy, delta G, just like you can delta H of formation, okay? So this, again, is very similar to what we've already talked about. The equation here, you can probably guess what it's going to be. The delta G for a reaction is sum of the delta G of formation of the products, and I left out the N and the M here. I'll come back and get those in a second. Minus the sum of the delta G formation of the reactants. Okay, so it's just like the delta H, products minus reactants, and then you've got your N here and your M here. Okay, actually I may have put those in the wrong place. Maybe they should go inside the sum. I can't remember. Basically, you just multiply the one reactant or product by its coefficient, right? You guys know that, so I think probably it goes on the inside. But basically, this is just a products minus reactants thing, just like we've done before, okay? And you just make sure that you multiply that each of those numbers by its coefficient in the chemical equation, okay? All right. So delta G for any element or molecule in its standard state is going to be 0. That's the same thing as with delta H, okay? And so same thing that we had before, where delta H is 0. When something is in its standard state, okay, which is at 25 degrees Celsius, and that's when we're talking about just an element or a molecule like O2 at 25 degrees Celsius, its delta G is 0. Okay, do you guys remember talking about that with delta H? Okay, so you just have to remember when it's going to be 0, okay? All right, so sample problem here, calculate the standard free energy change for the following reaction at 298, and I gave you some delta G's here, okay? Actually, I just gave you 2 delta G's. Is that enough? Probably. Which one do we not need to know a delta G for here? You guys see that? The Cl2? That's in its natural state, okay? So that one's going to be a delta G of 0. So then we just take the products minus the reactants. The PCl3 is negative 269.6. And then we have to multiply, that's kilojoules per mole. Okay, and we have to multiply that by 4. Okay, and then we have to subtract that from the, or subtract the reactants from that, I guess I should say. So then we've got 24.4 kilojoules per mole. Times 1. Because there's just a coefficient 1 there. Okay? So once we work that out, I'm getting negative 1102. .8. And we're doing addition subtraction here, so I guess that's our correct number of sig figs on this one. And that's going to be kilojoules, okay? So what does that tell us about whether this reaction will happen spontaneously or not at that temperature? Yeah, very spontaneous, right? Okay, so that's, again, that sign can tell us something about the spontaneity of the reaction, which is useful. The standard free energy change for the reverse of that reaction would be, any guesses? I mean, we can recalculate it, but essentially you just flip everything, and if you flip everything, what's going to happen? Yeah, it's going to be positive 1102.8, right? Okay? So you can kind of manipulate these equations the same way, or you can manipulate delta G, I should say, the same way that you manipulated delta H, right? If you flip the equation, it changes the sign. If you double the equation, it doubles the delta G, that sort of thing, okay? So that's all kind of useful. All right, look at the following reaction. Without using any data or calculations, predict whether delta G for this reaction, I shouldn't say for this reaction, is more or less negative than delta H. Use the following data to calculate. Okay, so let's do that first, okay? Predict whether the delta G is more or less negative than delta H. What does that mean? here's our delta H, okay? What's the other thing that has an effect on delta G? Delta S, right? Okay, so our delta S here, what's happening to the entropy of this system? Is it decreasing or increasing? Do we agree with that it's decreasing? Okay, it looks to me like we have 6 moles of gas on this side, only 3 moles of gas on this side, plus we have a liquid now, right? That looks like a decrease in entropy to me. So let's think about our equation here. Delta G equals delta H minus T times delta S. Okay, so we've got our delta H. We already know that that's negative, right? If our delta S is also negative, then what does that do to our overall expression here? It's going to, say it again, it's going to increase the delta G. Does that make sense? Because this is a negative T delta S, so if you multiply a negative by a negative delta S, that's going to actually make this term right here positive. Okay? And so you're adding that to the delta H. So that's going to make the delta G actually less negative than your delta H. Okay? So you can kind of just think about it conceptually. Now we're going to go ahead and calculate this. Oh, and it says use the following data to calculate the standard free energy change for the reaction at 298. So then it gives us the delta G's of formation, rather than giving us the delta S of this one, which that's the other piece of information we would need in order to solve it this way. But they're giving us the delta G's of formation instead. Okay, so we've got CO2, where's the CO2? Negative 394.4 kilojoules per mole times 3 moles of that. Gonna be a little lazy with my units here. Plus we've got the H2O, negative 237.13 times 4. And then we're going to subtract the reactants from that. Now, again, the O2 is going to be 0, okay, because that's its standard state. So we don't need the O2, we just need the C3H8. And that is negative 23.47 kilojoules per mole times 1. Okay? So negative 394.4 times 3 plus negative 237.13 times 4 minus 23 plus 23.47. Negative 2108.25. Again, because we're adding and subtracting here, let's go with, I guess I'll round that to 0.2 kilojoules. Okay? So was our prediction correct here? Is that actually less negative than the delta H? It is, okay? So that's that. All right, hopefully that makes sense. We'll talk a little bit more about Gibbs free energy in the next couple of days.